turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists, the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith, and this week, as NASA's Europa Clipper mission successfully blasts off towards Jupiter's moon of the same name, we're looking at how it leads the search for life elsewhere in our solar system.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
A NASA spacecraft called Clipper will spend the next 6 years voyaging, hot on the heels of a similar European probe called JUICE, which is also bound for Jupiter, to visit our largest planet's mysterious moon, Europa. An important goal of the mission is to determine whether this icy satellite, which is nearly the same size as our own moon, might be home for alien life. Europa, which was first discovered by Galileo Galilei in the early 17th century using his homemade telescope, has long fascinated space scientists owing to its unusual geology. Close proximity to Jupiter means it gets gravitationally stretched and squeezed, generating sufficient heat, scientists suspect, to form a liquid ocean tens of kilometres deep that sits beneath a thick icy shell. Periodically, plumes of this seawater erupt from the surface, and scientists like Lawrence Roth, who's at the KTH Royal Institute of Technology in Sweden, have built instruments that are aboard Clipper and can scan these plumes from orbit to discover what they're made of. He was at the recent launch at Cape Canaveral in Florida.
I was there, and it was the very first time that I did see such a launch. I was quite excited. It was meant to happen on the 10th of October. I flew there a couple of days earlier. Then we've all heard about the Hurricane Milton coming through Florida, postponing the launch, so we had to wait through the hurricane, and finally the launch pad, Kennedy Space Center. So the first man on the moon were launched from the same place Europa Clipper was launched.
4, 3, 2, 1, ignition, liftoff. Europa Clipper, separation confirmed.
There we go.
Takes like a minute or two. You see it going up. It looks like really like an explosion, and then, well, we were 10 kilometers away, so the sound takes like half a minute. You get a huge sound wave. You see it going up, and a minute later, it's gone, and it's on its way, not directly to Jupiter, first to Mars, and then actually comes back to Earth, and then it goes out to Jupiter, and that is mostly to use Mars to accelerate, to get faster. But it's been really, really cool to see it happening and going on a very nice sunny day then in Florida.
This thing we call Europa, what is that and where would I find it in the solar system?
So Europa is, as some say, the second moon of Jupiter, is one of 4 large moons of our largest planet in the solar system. There have been space probes visiting the planet, and most of all, a space probe called Galileo, like to discover orbiting Jupiter, every time taking pictures and probing electric and magnetic fields in the environment. And then all this information together tells us all these things. What is in the surface? What is even below the surface? What's the gravitation that pulls on the spacecraft from this moon? And this together gives you a good picture like we have today.
Do we know, or can we postulate how Europa came to be? Because, for instance, we know the Earth's moon was probably formed from a collision event between the early Earth and another small planet. Where did Europa come from?
That's a very interesting thing, because we have different kinds of planets in our solar system. We have gas planets like Jupiter and Saturn, for example, and then we have terrestrial planets like the Earth or Mars or Venus. So these terrestrial planets like Earth, they usually do not have moons. The moon of the Earth exists because we think there was a collision. The gas planets on the other side, they have moons, and they kind of all have always been there since the beginning of orbiting the planet. The strongest evidence, I guess, is that these moons are orbiting in the same plane as the rotational plane of the planet, which makes most sense if all is formed at the same time. If you have an object that has been captured later, come in from a random direction, just happen to come too close to Jupiter at some point, and then the heavy Jupiter captures it, then it rather has kind of a random orbit, quite eccentric, so not a circle, but an ellipse.
And what's been your interest in the Clipper mission? How did you get involved?
So I'm part of the team that built the UV spectrograph. It's a camera that can break light into wavelength, into its color, so to say, but it's ultraviolet light, so it's not light we can see with our eyes. This camera was built by the Southwest Research Institute, a place in Texas where I worked before. This is the method we use to study moons, in particular the atmosphere around the moons, which you can probe very, very nicely in UV light.
Is there much of an atmosphere around Europa then?
It's a very tenuous or dilute atmosphere. There's not much at all of an atmosphere. It's more than 10 orders of magnitude lower pressure on the surface of the moon compared to the surface of the Earth. No one can breathe there. You could basically feel like it's a vacuum. But it's enough of an atmosphere that you can study it and that you can learn about exchanges, what's coming from the surface, what's been lost into space, which is an interesting part of the whole system of the moon.
If we talk again in X number of months' time, what are you hoping to be reporting to us?
It does take 6 years, so it's a really long time. That's quite different from other. Often you send things to space, and if you only go to Mars, it takes a few months or even closer. Now we have to wait for 6 years until we really can learn something about Europa. And I mostly want to be surprised, because I think that's kind of the thing. We can make some predictions, and we have models, and we can say, oh, we expect this, and we expect the atmosphere, and we expect this, and we think there's liquid water and stuff like this. But I'm mostly kind of hoping for many surprises. I can't tell you which, obviously, but I wanna see things that are different actually than we expect today.
And there is nothing the scientists relish more than a result that they weren't expecting. That was Lawrence Roth at the KTH Royal Institute of Technology in Sweden. But why do scientists think there might be life on Europa? And would it look the same as it does here on Earth? Here's Adam Frank, a physicist and an astronomer, and he ought to know the answer to those questions because he's also the author of The Little Book of Aliens.
By aliens, we mean any life that has formed someplace else other than Earth. So, microbes on Mars, the possibilities of animal life being evolved on alien planets, distant exoplanets, or the possibility of life forming in the ocean moons that orbit Jupiter and Saturn, which is what Europa is one of.
Why does Europa matter?
Well, so the important thing about Europa is it is a moon of Jupiter. It is a little bit smaller than our moon, but here's the amazing thing about it. When we sent space probes past Europa, what we found was there were virtually no craters on it. And there were no craters because it was ice. The entire planet was covered in a 10-mile thick layer of ice. And below that was a 100-mile thick ocean. So Europa is a water world, essentially, with a thick covering of ice in it. And there's more water on Europa than there is on Earth, by a factor of 2, actually. So what that means is, because we believe that water is essential, liquid water, for forming life, there may be other ways that it happens without water, but we really believe water is probably one of the best ways we can think of for life to form in. That Europa is a great candidate for the possibilities of life in the subsurface ocean. And we can talk more about how that can happen, but that is really what it is. There's so much water that this seems like a really great place for us to think about alien life forming.
Given it's millions of miles from the sun, and most of the other entities around there are very, very cold, why is there liquid water there at all?
Yeah, this is a really fascinating idea. It's because of what we call tidal forces, which really, it's the same thing that's happening with the moon and the Earth. Jupiter is huge, and it exerts gravitational forces on the inside of Europa that heat it up. The gravity is constantly tugging and pulling and squeezing the inside of Europa, like silly putty, like just taking silly putty and squishing it back, or clay and squishing it back and forth. It heats up. And that heat is radiating out into the ocean, keeping the water from freezing. So it is this heat flow driven by Jupiter's gravity that's coming from the interior of Europa, radiating out into its surrounding water that keeps the water liquid. And more than that, what we expect is there could be vents, places where molten rock is spewing up to the surface of the ocean, the boundary between the rocky part of Europa and the liquid ocean. And those deep sea vents are exactly the place where we think life could start. It's been hypothesized that's how life started on Earth, at deep sea vents in the Earth's ocean. So that's really why we think life could have started on Europa, billions of years ago, and maybe now Flora has evolved into a complex ecosystem.
Essentially, that's like Darwin's warm little pools, isn't it? These hot springs. If that is the kind of environment with all the chemicals and raw materials arriving that might facilitate life, what's going to power it, though? What would life rely on for its energy source, if not that heat?
It would be the heat and the chemistry that is possible in that heat. So, you've got this upwelling of molten rock, which has all kinds of compounds in it already, sulfurs and metals. And when they hit the water, all kinds of chemistry, as I like to call it, chemical shenanigans, goes on. And that is a beautiful place to start powering biochemistry. And so you get biochemistry at these deep sea thermal vents. And then from that, you can start evolving larger and more complex creatures. When we send deep sea probes down to these deep sea vents on Earth, we find these amazing, crazy ecosystems of creatures we've never seen anywhere before, all living in the surrounding of those deep sea vents. So they themselves can power rich ecosystems.
How are we going to investigate this, though? Because given the scale that you've outlined for us, the amount of ice that's there, the huge volume of water that's there, and if all this is going on underneath all that, how are we going to see it?
Yeah, that's a great question. I mean, what you really want, the cool thing would be like to land a nuclear-powered heater that would just melt its way, through the 10 miles of ocean. But that's not going to happen anytime soon because we don't know how to do it. So what we're going to do right now, at least, how we're going to get started is we're going to send a probe that's going to do flybys, multiple flybys around Europa, getting very close to its surface, and then turning a bunch of instruments at the surface. And what we can already see, is that the surface is a bunch of cracked plates of ice that are grinding up against each other. And on those cracks actually have different colors than the surrounding ice, because what we think is happening is at those cracks, you're getting liquid water from the ocean 10 miles below, upwelling and making it all the way to the surface and refreezing. And so that is new ice, basically, that carries compounds from the water or from from deeper below the ice. And so by investigating the compounds we're going to find on the surface, we'll be able to tell whether are those the kinds of things we expect from life. Maybe we'll be even able to tell that there's stuff in those ridges that actually is life. I don't think we're going to be able to get there, but we're definitely going to be able to investigate these places where we think we're seeing indirectly water from the ocean.
What would be the hallmark then of life? If you find particular traces or chemicals, what would be the ones that unequivocally say to a scientist, that's a life process that produced that?
Yeah, that's a really interesting question, which people are going to argue about. I mean, to the first order, you kind of would love to find proteins or something. You would like to find large, complex molecules that you think were indicative of being assembled, by life. But even before that, you might just want to find, even the building blocks of amino acids and things that are, because that would indicate that there were biochemical processes going on there. But, as we've gone on, as we've become more sophisticated in our thinking about this, we're also thinking about things that, the life could be totally different. We shouldn't expect it's going to look like Earth life. So people have been thinking about, like Sarah Walker and collaborators, about the idea of agnostic signatures of life, like just looking for molecules that are big enough and complex enough that we don't think that nature without life could have produced them. So we are thinking about the possibility of how would you identify a molecule that looked that came from a very different kind of life, but still something about its structure told you like, only life could build something that big.
It's so exciting, isn't it? Adam Frank there, author of The Little Book of Aliens.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith, and this week we are hearing about the Clipper mission to Jupiter's moon, Europa. Still to come, what does the scientist who landed the first probe on a moon of Saturn make of this project? But first, we're going to take a closer look at the project itself, and there's perhaps nobody better to help us than Brittany Schmidt. Brittany's an Associate Professor of Earth and Atmospheric Sciences at Cornell University, and she's played a major role in the Europa Clipper mission. She's been speaking to my colleague, James Titko.
On Europa's surface, we have only about 10% of it covered in what we call high resolution. But in this case, high resolution is anything greater than about 300 meters per pixel, which in most images you would miss the building that I'm sitting in. Compare that to Mars, where most images you would probably see my laptop. So we've got a lot of work to do. So one of the things that Clipper will do is just get really, really in detail. We're going to have better than 100 meters per pixel coverage of most of the surface. We'll get better than 10 meters per pixel over a significant portion of the surface. And that's going to allow us to do things like see the surface up close and think about where we might land in the future. Along with those camera images, we'll be getting spectrometry, so telling us what the surface composition is all about. We'll also be getting temperature readings of the surface, and we'll be getting ice-penetrating radar at the same time. And that's kind of like taking an X-ray of the ice shell. We'll actually be able to see into the deep subsurface, potentially all the way down to the ocean for the very first time. Then we add in the magnetic field data that'll give us a chance to understand the depth and potential salinity of the ocean. Then we've got this really amazing synergistic picture of how Europa works and where we might go in the future to actually start this real search for life.
Unfathomable, the sort of level of detail you're describing for something so many hundreds of millions of miles away. The Europa Clipper mission is obviously, focused on Europa, the moon of Jupiter. But it's not going to be orbiting around the site of most interest. It's orbiting around the planet Jupiter itself. Why is that?
Well, this is a great story, and it's actually why Europa Clipper is so interesting. When we thought about sending a mission back to Europa, we all imagined that it would be an orbiter, that we'd go in and we'd orbit Europa and get really close to the surface. Jupiter has these huge radiation belts, and Europa lives inside those radiation belts. And so it's a terrible place to be a spacecraft. So by actually doing these unique orbits that we call crank over the top orbits, it allows us to do the same science that you would do if you were orbiting Europa, but it allows you to do it by doing multiple different flybys. And so we're going to fly by the surface of Europa during the prime mission with about 50 close flybys. So that's within 100 kilometers or so of the surface. So we'll get in close and then we'll do a burn and leave on a different trajectory. It also means that we can send back all of our data because we get out farther away, we can radio back for long periods of time, and we don't have to live in the radiation belt. So it also allows us to use solar panels. So it really helps the mission with its lifetime. We'll be able to take more data, probably survive longer, potentially have extended missions, all because of this different style of orbit that we wanted to have for this mission. And so it's a really kind of a tale of innovation in how we think about orbiting spacecraft.
So we have the probe transmitting information back to Earth while it's out of the harmful radiation in the immediate atmosphere of Europa. But let's go into a bit more detail there, if you don't mind. I mean, what the actual practicalities are of communications between the Clipper probe and the teams back here on Earth.
Jupiter's really far away. It's 5.1 astronomical units from the sun. So it's 5 times as far from the sun as we are. And so it takes between about 30 minutes and almost an hour, depending on where Jupiter is in its orbit, for signals to reach the Earth. And so we have already planned out most of the orbits. We can tweak it, and so we'll be able to respond to what's happening, but we have this great plan already in place that allows us to kind of just execute when we get there. And on board the spacecraft, we have the ability to pre-process data to either compress it or to make decisions about what to send back first.
The dream would be for that data it's sending back to show some evidence of life. But as you kind of alluded to earlier, it's not really designed specifically for that per se, is it? It's more looking for the signs that life might be possible, that the moon might be able to support life. More likely, the hope is that this sets us up for a future mission where we can perhaps get a lander on the surface of the moon.
Yeah, exactly. We're going to be able to understand its chemistry better. We're going to know where water is inside the moon. Are there places where it's really close to the surface that we might go down and explore? Are there plumes coming off of the surface that we can get in close and sample the chemistry of? So we'll get some indications that might point in the direction of life, but it's really, really complicated. Planets are complicated beasts. Very famously, the first life detection experiments that went to Mars, depending on who you ask, are kind of failures because we didn't know enough about Mars when we asked those questions. We sent experiments that reacted with the atmosphere as opposed to being something that organisms were eating, for example. And so one of the things that's really important and that we've learned in planetary exploration is that you really need to understand the system very well in order to design a good search for life or a good experiment. And that's true in any kind of science. And so what we're doing with Europa Clipper is we're taking several leaps from what we understood with Galileo, much better chemistry data. Famously, the Galileo spacecraft didn't handle the radiation environment very well. And in particular, the chemistry instrument, the spectrometer, really didn't. And so we have open questions about what the surface is made out of, what the salts are made out of, what are these dark patches on the surface. And so we'll get a chance to see that. Finding a place to land, finding really cool places to explore, and places that are likely to have that kind of process going on, energy for life, that's what we're really looking for.
I almost want to go there and see it for myself, apart from the downside, as Brittany alluded to, that you do get a lethal dose of radiation in less than a day at the surface, I've since found out. That was Brittany Schmidt. She was in conversation with James Titko. Well, finally today, we're going to take a look at the big picture. What might determine the success of this project, and how is the Europa mission pushing the limits of what we're able to do in space these days? John Zarnecki is Professor of Space Science at the Open University, and he's also the former director of the International Space Science Institute. He and I first met many moons ago when he visited Cambridge University to talk about his involvement in the Cassini-Huygens mission, which put a probe on Saturn's largest moon, Titan. I began by asking him how that mission 20 years ago differed from this one.
It's different. It's not trying to land, but it's a very challenging environment because Jupiter is one of the worst places in the solar system from the point of view of radiation. It's coming from the very strong magnetic field around Jupiter, the magnetosphere. And in that strong field, particles, electrons, other charged particles, get accelerated to very high energies, and these then smash into your delicate instruments. So what Clipper is going to do is to go into an orbit, which means that for a lot of the time, it'll be quite a long way outside of the damaging regions, and it will then dive in and pass relatively close to Europa, take its measurements, and then go back out on its orbit.
How can you simulate what it's going to experience on its way to a place like Saturn, or in your case, but Jupiter in this case, so that you can give it a trial run before you actually have to put this thing in space? Because if you're building it once, you've only got one go. If it's going to take 7 years to get there, you've got one chance. How do you make sure it's as foolproof as it can be? Do you literally dunk these things in liquid nitrogen to see how they handle cold temperatures? Do you blitz them with radiation in the lab to see how they handle that sort of thing? How do you do that? How will this team have approached safeguarding that aspect of the Europa mission?
Well, Chris, it sounds as if you're a rocket scientist already, because we do exactly what you've said. In fact, there are two types of approaches one takes. One is the physical testing. For example, what we call thermal vacuum. So we put the instrument, or in fact the whole spacecraft, in a big vacuum chamber, and we expose it to the extremes of temperature that it's going to see. In fact, we over test it. So we go hotter and colder than it will actually see. We will shake the spacecraft. That's a horrible test when you see your delicate instrument, you see it being shaken mercilessly. That's to simulate what happens on launch. You often do an acoustic test because also at launch there's an enormous level of sound which can be very damaging to equipment. The other thing that you do, and this is increasingly so, you run computer models. So a good example of that is what's called thermal modeling. In a computer, you can expose your equipment, your materials, and the structure to extremes of temperature. But it's really a combination of the two approaches.
And assuming all that goes to plan and you get to where you're going, in this case, we're hoping Europa in 6 years' time for this mission. To what extent is the mission baked in from that point? You have to follow a specific research program. And to what extent will they have the flexibility to adapt the mission once unforeseen things happen, other exciting things present themselves? Because that's what we're in the business of doing science for, isn't it? Because there will be things that are uncovered that then lead you down a rabbit hole that you hadn't foreseen.
Absolutely. So the mission, to a degree, is planned out already. When we arrive at Jupiter, that will be the expectation. But you can be almost certain that things will happen. So there'll almost certainly be some technical aspects that won't work quite right. And this is where another aspect of the design will come in, and that is redundancy. So some physical aspects of the spacecraft, for example, transmitters, they're probably doubled up. So if one fails, you can switch to another. But there might also be good things happen by that. I mean, some particularly exciting feature might be found that we hadn't known about, and which might, for example, give us access or the possibility of accessing material from the subsurface ocean. So that will mean a change to the orbit to access that region. Having said that, at least initially, my experience is that all the mission operations people, they're very conservative in their approach. And so certainly early on, they will minimize any risks taken. But you can be pretty sure that as the mission evolves and they become more confident of the spacecraft, how it operates, that they'll be prepared to take more risks. And the really exciting part comes towards the end of the mission. I would be very surprised if in the last few passes of Europa, they don't go for a very, very close flyby. And if something goes wrong with the targeting, there's a possibility of crashing into the surface. But, as the mission goes on, certainly greater risks will be taken.
We'll actually end up with 2 probes in the Jovian system, won't we? Because we'll have the Clipper mission, which is the one that's just blasted off. We'll also have the other one, JUICE. So we'll actually have a pair of probes there. Does that offer any opportunities? Can one thing inform what the other one then does?
Yes, there's absolutely no doubt about that. So JUICE, that's an ESA mission, European Space Agency mission, which was launched last year. And they are going to be in the Jovian system at the same time. But the emphasis of JUICE is on the moon Ganymede. So Ganymede is the largest of Jupiter's moons. In fact, it's the largest moon in the solar system. The belief is that it has also a subsurface ocean. So, to me, I think the fact that these 2 missions are going demonstrates, I think, that the scientific emphasis in the study of the outer solar system has shifted in the last 20 years towards the study of these icy moons about Jupiter and Saturn rather than the massive planets Jupiter and Saturn themselves.
So what does then success for you, given your pedigree and form in this area, but what does success of this mission look like to you?
Both of these missions have the potential to, I would say, confirm beyond reasonable doubt that these oceans absolutely do exist. So success would be if we get incontrovertible proof from Ganymede or Europa, or perhaps both, that we really do have these oceans below the surface. And then, of course, we can start thinking of 20, 30 years hence of sending a mission which somehow can get down below that ice and into the liquid.
Well, you're sort of retired these days. You've got some time on your hands, John.
Well, I've said to you before, Chris, the rocket science is great, but it is, I would say, it's mostly for the youngsters because it just takes you over. You know, it's body and soul 24/7. So I think it's the youngsters' turn to burrow below the ice and get into the oceans. I'll be watching, though, from afar.
As will we all. That was John Zonecki from the Open University. So it is bon voyage to the Clipper probe, and do be sure to join us in 2030 as the data start flooding in. Indeed, will our hypotheses be proved right that a hot, chemical-rich salty water is there and a good place for life to get started? What will the surface terrain look like? And what will those plumes reveal about what might lie within? Watch this space. That's it for this week. Next week, as we ramp up for a pivotal US election, we'll be asking whether tech and AI might influence the outcome of that closely fought race. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith, and from everyone here at the Naked Scientist team, thank you for listening to us, and until next time, goodbye.